Recording. Good. So session 3 of the logistic regression session. As I was saying just now, we've covered so far what a logistic regression is. What it is a way to model a logit. A logit is the log odds of something happening. Remember, the odds is the ratio of the probability of something happening to the probability of something not happening. And the logarithm of that is the logit, for some reason, because English hates us. Right? And what we're trying to do is, when we model the logit versus a series of variables, is establish the coefficients of those variables and realize that if we raise those coefficients to the natural logarithm base e, that gives us an odds ratio. So at the end of the day, what we care about is the value of those coefficients and how robust this model is in terms of, when all this is taken together, how much does it explain the logit? How much does it explain the prediction of what's going to happen? So today what we're going to do is we're going to look at ways of assessing how strong that model is. So we're jumping ahead to the end. So far we've looked at what it is. We've looked at a little bit about the nature of the variables that go into it. So we said they can be continuous or categorical. And we said that the preferred categorical is the binary or dichotomous variable. We also said that ordinal variables are treated as if they're continuous. Right? And last time we also looked at, when you have a categorical variable, it's in reference to itself. So it chooses one level of that categorical variable and does references to it. For example, if you have socioeconomic status, you've got 3 levels, high, medium, and low. And whatever odds ratio it gives you, it's going to be high relative to low and medium relative to low. Okay, so that's an important consideration when you interpret the findings. Now, what we should be doing next is things like analyzing those variables to see what kind of changes we need to make to figure out if they're skewed, if they're bimodal, if they need to be transformed. We'll get there eventually. What we should be doing after that is figuring out if there's interaction or confounding. We'll get there eventually. Instead, I'm going to jump ahead to the very end so that we know. Because it's easy, that's why, really. So the diagnostics is actually easier than the other stuff. So, but it looks harder. It's got fancier names and some new things that may scare you, but it's not scary at all. Okay. Other thing I want to point out is I'm covering this stuff at a very superficial level, even though it may not seem that way. And I encourage you to do your own reading and to go deep into it yourself. For example, I'll mention things like likelihood ratios and walled statistics. And I'll define what these things are, but I'm not going to spend a lot of time talking about them. So if you think these are important, do your own reading and go deep, especially when it comes time for defending your thesis, in case you get an asshole in your committee who wants to know, what's a wall statistic? Well, you know. So there we have it. All right. Moving on. Today we look at testing the significance of the model or diagnosing how good it is. And what does how good it is mean? It means at the end of the day, we want an equation that allows us to predict these logits. So how good is the equation at predicting the logit? The best way to do that is to allow the equation to predict some logits, and then go back to see what the logits actually were that we were modeling and see how close they were. Because you're going to have things like, let's say we're modeling, like the example we've used so far is, will a candidate get elected, yes or no? And we have the factors like his gender, his income, whether or not he's an incumbent, his race, and so forth. To make that model, we use previous elections data and saw this guy got elected, he was white, middle-aged, male, whatever. That guy got elected, she was female, middle-aged, white, and so forth. So this is the existing data we use to make the model. We can go back now and apply these criteria and see what the model spits out for this guy here. We know he got elected. The model says, oh, he didn't get elected though, which means there's a disconnection there. The model wasn't very good at predicting this guy. So that's the kind of approach that we're going to use to see how good the model is. Ideally, we want it to be 100% good. SPSS is great for this, even though SPSS sucks in many ways, and real statisticians always badmouth SPSS. It's really good, though, for people who are new to this, because it spits out automatically the key diagnostics that we care about. So, review. Last time we talked as well about the kinds of entry that you can do with the logistic regression. So there's a backwards, forward, and simultaneous. And SPSS allows you to do different styles of entry. Let me pull this back so I can see as well. Okay, so for both backward and forward, it's going to give you the option of LR, which stands for likelihood ratio, conditional or walled. The walled statistic we talked about as well. Don't worry about it so much. It's just something it uses to determine significance. It's like a chi-square, but slightly different. And lastly, the enter. Oops. Ooh. How'd that happen? I forgot the touchscreen. Nice. Ooh, hello. Okay. So which ones do we care about? Really? Oh, come on. Really? There we go. So you're only really going to use the red ones there. Almost no one uses the conditional or walled versions, just likelihood ratio. So what these subcategories are the ways in which the computer decides what to keep in the model, right? And there are three different ways using, again, the likelihood ratio, something called conditionality, or something called walled. So don't worry about these two. Chances are when you do your study, you only care about the first one. You're probably only going to care about this bottom thing too. Hi, come on.
Oh, okay.
Hey, come on, sorry, yeah. Oh, you got my email, that's good. Yeah, it was some double booking. Anyway, so I'll back up slightly and say today we're talking about diagnostics. That is how to determine how good your model is at the end of the day, right? And the way we define how good the model is, I'm recording this so it'll be online later on, is how good it was at predicting the stuff you already have. Right? So how good the observed data is in terms of the predicted data. Right? So moving forward again, SPSS gives you three different ways to enter the data. The red ones are all the ones that you will probably use, and probably you're only going to use the enter or simultaneous one. If you're being a little more ambitious, you'll probably use the backwards method. Unlikely you use the forward method. It's unlikely you're going to use the ones in black. So to remind you what these are, the forward method is when it looks at the equation you want to make, the super variables you have, looks at the first one, does it fit? No. Next one, does it fit? Whatever. And in the backwards, it starts with all the variables together and tests each one individually. I take it away, is it good or better? I'm not sure. If I take it away, is it good or bad? I'm not sure, and so forth. And it runs through this a certain number of iterations. Usually about 20 is the standard we use. Okay. By the way, if it finds, after a number of iterations, that the model isn't changing that much, it stops trying. It says, there's no point going on. This is your final model. We'll stop at 6, whatever. And then enter is the standard way. Okay. So I can't even see this anymore. All right, so before I go to significance testing, we're going to just review how we start the process a little bit. I've stolen a lot of the images here from an online source, and I've given, reference for it, so it's not plagiarism at all. Okay. And by the way, I've added some resources to the website. I encourage you to go through them quite thoroughly because there's a lot of step-by-step stuff there. In case I miss it, it's really well explained in the resources I've added. All right, so we're going to use the homework question from last week as our example, and I'll assume you all did it. All right? At the very least, you downloaded that data set and you just ran regression and see what you got. At the very least, it's 5 seconds of trying stuff out. And again, even though I know most of you didn't do it, you know that in the data set, it was a bunch of people, students, who were judged on their reading scores, their math scores, their science scores. We had their socioeconomic status, their SES, their race, and so forth. And then I asked you to create a dichotomous outcome variable, and we called that HONCOM. Why do we call it HONCOM? Because I stole this off the internet, and they called it HONCOM. So if you Google this, you'll find everything is right there. And I said, define your outcome as whether or not someone got more than 60% on their reading test. If they got more than 60%, we'll say they're an honors communication student. Right? And the way you do that is you go to the transform or compute command in SPSS and say if reading test is over 60, then HONCOM equals 1. If it's not, then HONCOM equals 0. So you have a dichotomous variable there. Then I ask you to run a regression that predicts whether or not this is an honors student. So basic stuff. So that's what we did. So you take my glasses off here. If you didn't figure it out, that's how you get into the system. You click on regression, you select binary logistic. You note there's all other kinds of regression here. We're doing a binary logistic. And then there, you've got some variables to select. You move the outcome one into the dependent window, because that's the thing that we're trying to model towards, a dependent variable. And we move the ones we care about modeling into the independent or covariate box, right, like that. Now from here, you have to decide which of these is a categorical variable. We did that last time, because remember, categorical variables are very special. Ooh, what's this? It says something about, right, okay. So if you notice here, there are these arrows here that says next and stuff. That's because you have the option as well of entering data in blocks, all right? I don't want to get into that because you probably won't be doing that. Here it asks for the method of regression. We said there's enter, backwards, and forwards. We're going to do enter right now. If we had backwards and forwards selected, then you'd have the option here of entering blocks. And what that means is, I mentioned that you can enter one variable, it looks at it, second variable, it looks at it. You can enter a bunch at once, then it looks at it, a bunch at once again, and it looks at it then. Those are called blocks, okay? So one of these screens represents a block, press next, another screen represents a block, and so forth. Don't worry about it. I'm guaranteed none of you are doing that. That's a bit complex. Right, so focus on the other stuff, right? Once you've identified your categorical variables, you can open the categorical screen, and it moves over here. The ones that, ooh, stop touchscreen, stop that, get back there. Okay, so the ones that you think are categorical, move it over here, and it's going to ask you the characteristics of those categorical variables. Remember, the computer doesn't know what's categorical. You have to tell it. The computer's dumb. Do not rely on the computer to do the math for you. I'm going to say that several times because when we go through the various types of diagnostics, they'll all tell you something different. They'll say, oh, this is great. This is not great. This is great. This is not great. And you'll say, which one do I use? Well, that's where the intellect comes in. The computer doesn't know. It just does the numbers. You've got to choose. But I'm ahead of myself. So you move over the categorical variable, right? Let's say that one's categorical, and you select what kind of categorical variable it is, the kind of contrast. We said last time you want indicator contrast. You don't want deviance or anything else. That's the standard method we usually use, and I guarantee none of you is using a non-indicator method. It's also going to ask which level in that categorical variable is the reference category. Usually it's the last one. In the case of the homework question, there's socioeconomic status. The first one was low socioeconomic status, the second one was medium, and the third was high. That means that we usually want to compare things to the lowest. So in that example, you want the first one to be the reference category. So you have to know your variables fairly well to know what the different levels are. Okay?
So sorry, if you're comparing it to the 0, it's first.
0 would be yes. Yes.
Okay.
Yes. Okay. Okay. Now, before you click do the regression, before you click OK, click on the options. And this is where we get into the diagnostics portion. The options, look at all these options here. There's classification posts, there's Hosmer lemme, there's Casewise listing, all the stuff that sounds scary right now. We're going to go through these today and to show you that they're not that scary. They sound exotic. But the important things to choose are these. Choose the classification plot, choose Hosmer lemme, choose Casewise listing, and choose confidence interval for e to the b, because that tells us the confidence interval of our odds ratio. E to the b is our odds ratio. We need to know the confidence interval. Notice over here it's asking for the entry and removal numbers. So if you're using the simultaneous entry method, that's not relevant, because in simultaneous entry, all the variables go in at once. If you're using the stepwise method, that is forward or backwards, where you're adding some, then taking some away, it needs to know how sensitive it should be to either keeping variables or taking them away. So if you're going the forward method, it's going to look at a variable, it's going to analyze it using a particular method. That method we showed in red earlier, the LR versus the conditional in the world, is where it comes in, right? It's going to use what's called the likelihood ratio method, if you chose that LR, and it's going to say, based upon that entry criterion, here it says 0.05, if my thing is at least my relationship with this outcome variable is at least a significant level is 0.05, it goes in. If it isn't, it doesn't go in. So that's my entry characteristic. If I'm using the backwards method, and the backwards method, again, is all the variables go in at once, and it looks at one of them and says, I don't know if this is good enough. It does its independent testing, and it gets a p-value. If the p-value here is that or less, then it stays in. Here is 0.1. Okay? So remember from basic stats class, you want the p-value to be as low as possible. P is low, that means great significance. We're flexible here a little bit because we don't want to make the threshold so extreme that nothing stays in. So if you're going to use a stepwise method, this is the go-to numbers, but sometimes you want to be a bit more permissive to let your variables in. So maybe you want to raise that removal barrier to 0.2, so anything that's 0.2 and under stays in, right? I personally use 0.2 using stepwise because I like to fudge it a bit to make sure things stay in. But anyway, if you're not using a stepwise method, this is not relevant to you. But be aware that that's what it's there for. Anything here that needs to be talked about? Not yet. Okay. Move forward. All right, let's look at the output now. I can't see what I've written here. When you do the output of the regression analysis, you'll see a bunch of fun things that will scare you, but they're not scary. We're going to go through the pertinent blocks right now. The first thing you'll see is this classification table. If you can't see that, you have the slides in front of you, I hope, right? Here's the two levels of the outcome. Here is the two levels of the outcome again. What does that mean? These two are the actual data. This is the predicted data. Because I mentioned we're going to compare the predicted to the observed, right? And it shows that in my observed data, the actual data that I have, for the ones that are honor students, I get 132 plus 15, so 147 total honor student. Right? And in my data, I have 26 plus 27, that's what, 53 non-honor students. The model predicts, however, that I'm going to have 132 plus 26, 158 honor students, and here it's going to have 42 non-honor students. Kind of close, but not exactly right. What do I do with that? Well, it's already separated here so you can figure out the percentages. So it's 89.8% correct for the honor students, and 15.9% correct for the non-honor students. If you remember your basic stats and basic epi, you can use this to compute sensitivities, specificities, positive predictive ratios, all that fun stuff. Think of it like a diagnostic test, like a screening test for cancer versus an actual lab test for cancer. So let's say you're doing the digital rectal exam for prostate cancer, and then you've got the actual, biopsy prostate cancer. How good was the digital rectal exam? You can compute a sensitivity number for it. So that's the first diagnostic you can do. It's not the best. It's the one that's most easily understood. So in your theses, I suggest you do all the diagnostics. So really impress your examiners. Look at all this great stuff I've done to show how good my model is. That's the first step. Here it gives you right away the total percentage of all the good stuff. So 79.5% correct, it thinks it is, right? Which is pretty high. So that's the first thing we do. In a perfect model, all the cases will be on the diagonal. So these two will be correct. Oops, damn. Back up, back up, back up, back up. No, I go forward? Where am I going? I'm going forward. There it is. Okay, but clearly it's not perfect. All right, the next thing you'll see is the most important box in your output is the variables in the equation. I'll go back a second. Okay, if I had an extra slide there. The variables in the equation is the thing that you really care about for your discussion and your outcome and all that stuff. And if you note here, the different columns, here are the variables that remain. If it was a stepwise process, some variables fell out. It said that, you're not fitting in based upon those criteria, fuck off, go away. If you're using the simultaneous method, they probably all stayed unless something was wrong with one. What could be wrong with one? A lot of missing values or whatever. Okay, so here we have all the names of the variables. Notice the, come on. Notice the categorical one here, SES, my one categorical one. It has these brackets here. That means it's labeling the different levels that you modeled. Also, the reference level is not on there. So in the case of SES, I modeled, I had low, medium, high, and I said I want medium versus low and high versus low. So low doesn't appear. That means the first one is actually medium, and the second one is high. Right? So the first one does not appear. The reference category does not appear. Even though there are 3 SESs there, the first SES without brackets is just the overall one, but it doesn't give you an odds ratio. It just gives you a p-value. So let's go through the columns. The first column is the coefficient of that equation. Remember, the coefficient is the log odds ratio. So you take e to the coefficient, and that will give you the actual odds ratio. The second one is the standard error of that coefficient. You probably don't need the standard error for anything. In the good old days, believe it or not, it didn't compute confidence intervals for you. You did it by hand. Can you believe that? Now it does it for you, so you don't need that standard error. Probably. The third one is the walled statistic again. You don't need that either. So just ignore it. If you want to know what it is, it was the test statistic that was used to compute the p-value. Okay, so maybe you've got a real asshole in your examination committee. They'll ask you, what is that about? Well, then just tell them. But in general, you don't need it. Next is the degrees of freedom. Again, at this level, don't worry about it. That's just for the relationship between each of these predictive variables and the outcome, how many levels of interaction were there. Don't worry about it. It's a confusing thing. Not even statisticians know what degrees of freedom are. We have formulas for it, but we all struggle to explain it. But the important things you care about really are these last 4. So the first one is the significance level. That's the p-value. Sig means p-value. And remember, if p is low, the null must go. You want low p. What's low p? Rule of thumb is less than 0.05. You can set your standards differently, but 0.05 is a rule of thumb. Okay, the next one is e to the b. So this coefficient risen as an exponent of e. And what does that give me? What's that? What is e to the b? I've said it 3 times today already. Nobody's paying attention. Guys paying attention.
Log odds ratio?
It is the odds ratio, right? So the b, the beta, actually, is the log odds ratio. So e to the b is the odds ratio. That's the most important thing when it comes to having a discussion with your examiners, because that's what they care about. All right, so let's look at it. This first one, you probably can't see it. It's 1.06. That's SES in brackets 1. SES in brackets 1 is that middle socioeconomic status compared to low. It says 1.06. Do you want to interpret that for me? You know what that means? If the odds ratio is 1.06 for the middle SES, it means for every increase in SES relative to the low that the medium has, the odds of getting the outcome increase by 1. Sorry, increase by 0.06. That's what it means. It's a tough interpretation, but this is what you got to wrap your brain around. So the odds ratio, anything above 1 on the odds ratio, is how much the odds of the outcome increases with every unit increase of the predictor. Let's try it again. Let's look at reading score. So reading score here, the odds ratio is 1.103. That means for every incremental increase in the reading score, the odds of being an honor student goes up by 0.103. That's what that means. What if it was 0.9? How do you interpret that? What if the reading score odds ratio is 0.9?
Decrease by 0.1.
Exactly. So the odds of being an honor student decrease by 0.1. Okay, that's what those are read. Notice the p-values here, they're all significant. In your model, they're not all going to be significant. And that's something you're going to have to want to talk about in your discussion. We can talk about that later, because today's not about the output. But I want you to show you this one thing here. So this is 2 levels of SES. One of them is 0.913, the other is 0.022. 0.913 is not low. That's not significant. 0.022 is. The thing is, though, when you've got a categorical variable, you've got like a bunch of levels here. If at least one of them is significant, they all are significant. Right? So you look for just one of them being, and they all stay in. That's an important consideration. Now, the last thing on this column is, the last thing, two columns are the confidence intervals. Hopefully you remember confidence intervals from basic statistics. These are 95% confidence intervals. You can use your standard error here to compute 99% confidence intervals if you want. But that's what these are for the odds ratio, to make your life a little easy. Okay.
Go back to the point, if one of them is significant, then it means the whole category.
That's correct.
How do we explain this in the discussion? What does that mean?
Well, it means that it stays. That's what it means, right? Because what you're going to do is only keep significant ones anyway. And I'll ask you, but Sahara, like your SES, that's not significant. Why are you talking about that? Because one of them is significant. That's what I'm talking about. It stays here.
Yeah, my question meant if you speak about this as a variable, so what does that mean? And what is the whole picture like? I don't understand.
What we care about is which variables are important to predicting the outcome. It means that the SES variable as a whole is important to predicting the outcome. That level might not be, but the rest of it is.
Sorry.
That's okay. That's fine. I want you to ask questions. That's good. That's good. All right. Okay. So the first thing you'll see at the output is something that says block 0, beginning of block 0, blah, 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 right? All that means is when you are doing the stepwise approach, it's going to enter things, it's thinking you're entering things in blocks. When you're doing just simultaneous approach, there's only one block you're entering, but it's still going to tell you that, hey, this is your block statistics. So the blocks just means all those variables that are going in at one time. Block 0 is always just the constant. Remember your equation has logit equals constant plus coefficient times something plus, right? If we're going to add things or take away things, block 0 is always just the logit equals constant. So block 0 is always there. Block 1, on the other hand, is the first one where you're entering variables. If you're using the entry or simultaneous method, block 1 is all you're going to see. Done. And you're mostly going to do that. Now, you're also going to see this. This is the omnibus test of model coefficients. Whew, what does that mean? If you're using a stepwise method, this will be a much larger graph with 3 things in each row. Okay, but here you only get one with one block of 3 things. That's because the simultaneous method only gives you one chunk of stuff. And this first thing says step, block, and model. The step is the step in which we are adding these variables. The block is the bunch of variables that we're adding, and the model is now we have this equation, what does it all mean? All right, why do we care about that? Because the way that the computer computes regression is in iterations. We throw all the stuff, we'll look at it, throw this other stuff, we'll look at it, and over again. Each iteration has a bunch of characteristics. For the entry level thing, entry and simultaneous, there's only one time we're doing this. That's why we only get one shot at it. So what step is it? It's the first step. Which block of variables? It's the first and only block of variables. And this is the first and only and last model that we're making. That's why it says that. Now, this has a chi-square, degrees of freedom, and significance. All right, what does that mean? The chi-square, you know what the chi-square is. Degree of freedom, don't worry about it. Significance that matters. So this is your second measurement of diagnosis or of significance of your model. And these p-values tell us, is it different from the model with just the constant? Is this block different from block 0, in other words? Of course it is. It better be. If it's not, you're in big trouble, right? So damn straight, that's going to be very, 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 that's why this p-value is so low, it's zeros. It's actually 0.0000001, but it only shows you 3 digits. Okay, so again, that significance says that we are tossing the null hypothesis. Which null hypothesis? In this case, the null hypothesis says that block 0 and block 1 are exactly the same. They're not. Toss that fucker, and we're different. That's what it means. There's going to be a bunch of null hypotheses we test here, and they're all kind of different. If it confuses you, don't worry about it. Just remember, in the case of the omnibus test, you want the p-value to be low, low, low. And it will be. If it's not, your thesis is over. Right? So it will be. Okay. What's the first thing? Next is the model summary. All right, that's a bunch of stuff. So again, it's done by step. So if you're doing stepwise, forward or backwards, you'll have multiple steps. If not, you'll have one step. And this shows us three things here. This says that -2 log likelihood. I'll explain what that means in a second. The next is the Cox and Snell R-square. And after that, I can't pronounce this, the Nagelkerke R-squared. A lot of fancy names, right? It's going to freak you out. Don't worry about it. Do you remember R-squared from basic stats? Remember what it means? Who remember what it means? Remember R-squared from linear regression or multiple linear regression? Nobody remembers. Okay. What an R-squared tells you is the amount of variation that your model explains. So if it was a simple linear regression, it would be y equals x, y equals some function of x. The small r squared would be the percentage of the variation in y that is explained by x. If it's a multiple regression with like y equals x plus y plus all this other stuff, it's the amount of variation that the super variables, the amount of variation in y explained by the super variables. Sure, yeah. Who's it now? Who's arrived now? Who could it be? Who could it be?
Sorry, are you guys out?
Yep, we are. Come join us, learn some stats. But in this case, the R-squared means exactly the same thing, except it's how much variation in the logit, again, that outcome, is explained by the super variables that you just modeled. So in other words, you want that R-squared to be as high as possible. The highest it can be is 100%, or 0.1. The higher the better. This one is 0.408. Is that high? Actually, it is kind of high. Yeah, it's kind of rare to find things, in my experience, like 0.6 or 0.7 or above. Again, it's not the end of the story if it's like 0.1, because I'm showing you lots of different diagnostic methods here. So it comes down to your creativity and your intellect to show, how they play together. But it's a good go-to system to go. So it's if we're not showing enough variation, it probably means we need more variables, more covariates to explain additional variation, right? This probably makes some of you a little nervous because maybe your data is insufficient. Maybe you're trying to predict the elections based upon someone's toilet habits, how often you go to the bathroom. Yeah, maybe that is predictive, but it's not sufficient. You need other things. You need their SCS, you need their age and the sex and all that stuff. So the R-squared will be low in those cases. All right, so that's important. Okay. So log likelihood. Now this is a difficult concept, so don't worry about it too much, but you'll hear that term come up a lot. Remember that I said if you're using the forward or backward method, you're going to choose the LR as the conditional method of adding or removing variables. The LR refers to likelihood ratio, or the log likelihood ratio. What's a likelihood? A likelihood is a probability that something happens in a certain scenario. In this case, the scenario is a hypothesis. Okay, what hypothesis? The null hypothesis. So what is the probability that this variable predicts this outcome if the null hypothesis is true? That's one likelihood. What's the probability that this variable predicts the outcome if the null hypothesis is false? That's another likelihood. Why do I take the logarithm? Because these numbers are actually really, really small. So I take a logarithm so it'll look bigger. Right? Now, probabilities range from 0 to 1. They're all less than 1. If you take a log of a number that's less than 1, do you know what that looks like? It's negative. So that means the log likelihood is always going to be a negative number. Why do we care about this? Because the ratio of those two likelihoods is how we assess whether or not these variables have any sort of meaning. Right? So if the hypothesis is false, true versus false, it's got one ratio. If it's true versus false, if it's false versus true, it's got another ratio. If I divide those two, then I'm getting ahead of myself. I'm talking about too much. So you want a higher log likelihood at all times. In this case, and because it's negative, you want the higher one on that scale. So -3 is higher than -7. Higher is good. Okay, so as I mentioned before, There are two hypotheses. First one, all coefficients equal 0. Therefore, the model does not predict the outcome. And the positive hypothesis is that coefficients are not 0. Therefore, the model does represent the outcome. Okay. I'm getting into theory there. It doesn't matter that much. If this confuses you, it doesn't matter. Just remember, you want the log likelihood to be high. Okay. Now, there's something called 2LL, minus 2L. Minus 2LL is the difference between the log likelihood with the predictors and the log likelihood with only a constant. All right, let me say that again. Remember we looked at block 0 versus block 1, and block 0 had just the constant and block 1 had the other variables? There are likelihood scenarios in both of those cases. So in the case of block 0, I could compute the log likelihood ratio between the null hypothesis and the alternative hypothesis in the case of there only being a constant. In the case of block 1, where there are lots of variables, I can compute the log likelihood ratio of one hypothesis versus the other. That's two numbers now. The difference between the two is minus 2LL. I bring this up only because when you read further, people will make reference to minus 2LL, just so you know what it is and don't get freaked out about it. It really doesn't matter all that much. Again, only if you get a really asshole examiner in your committee who's like, what is that? Your minus 2LL is off. No one's going to do that because no one really understands it. Okay, but when this is when you see those things come up. Don't get freaked out. It's the method it's using to figure out whether or not a variable has changed the relationship at all. Okay. In other words, likelihood ratio test measures whether the model has made an improvement in our ability to model the relationship. Okay. I wrote it down this way as well. I'd be able to phrase it correctly. So let me read it out loud here. The likelihood ratio test tests the difference between minus 2LL for the full model with predictors and minus 2LL for the initial null model with no predictors. I'm losing you. I'll move on. All right. So next one is the one that I prefer. This is the Hosmer-Lemme test, named after two guys named Hosmer and Lemme. And what the Hosmer-Lemme test does is it creates groups of respondents, of people in your data set, and compares the number of them that got the outcome versus the number that didn't get the outcome, and looked at the probabilities therein, right? So the important part is how to interpret the outcome. So the Hosmer-Lemme test will automatically give you this output. It'll give you two outputs. It'll give you a whole list of the block of 10 that it chose to analyze, and then it'll give you the outcome. It's a chi-square test with a p-value. Remember I said p-values are low, therefore they're good? This is a case where you want it not to be low. That's critical. For the Hosmer-Lemme test, you want to fail, because Hosmer-Lemme is testing whether or not, how do I put this? It's testing whether it's different from what it should be. Okay? So you don't want it to be different. You want it to be the same for what it should be. So you want that p-value to be over 0.05. And it probably will be. Okay, so with me? So bottom line is just scan it, look for a p-value, and you want to fail it. So here it's 0.778. We failed that test, therefore that's good. That means that model is not different from what we want it to be. Yeah? Okay, good. All right, cool. All right. All right, so I just said that in wider language. So if my words are confusing you, read the slides. I've explained it in more sober tones. Good. Right, next up is the classification plot. It is essentially a histogram of the frequency with which it has computed the logits. Right? So it's going to say, if in our example here, we're computing the probability of whether or not the student was an honor student or not, 1 or 0. And it's going to lay on top of that whether or not the student actually was an honor student, yes or no. And we're going to see a distribution. What we want is not a normal distribution. That would be bad, because The way the computer decides whether or not you are an honor student or whether or not the outcome happened is after it computes the probability and the logic and all that stuff, if the probability was over 0.5 that you're an honor student, then it says, yes, you're an honor student. If it's less than 0.5, no, you're not an honor student. So there's that very strong bifurcation of the 0.5 level. If the distribution is normal around 0.5, you're kind of screwed. It means it's all kind of hovering around the middle and doesn't know what and it's kind of random, really. So ideally, you want a U shape. Right? So let's go into that deeply. So by the way, over here in the options, the first thing you chose was classification plot as an option. Right? So in the following, I'll show you the graph in a second what it looks like. So the predicted probability is from 0 to 1, and those are ones, right? So the ones are the outcomes that we want. And the y-axis is the frequency, the 0 is the probability of it not having happened, and so forth. Right, we'll see in a second. Okay, things to look for. You're looking for a U-shaped curve. You don't want a normal distribution. And there should be few errors. That means when I show you the graph, this side will be zeros, this side will be ones, right? Because anything less than 0.5 didn't happen. Anything more than 0.5 happened. This should be all zeros over here. This should be all ones over here. If you got any ones over here, and you got some zeros over there, those are errors. We want as few errors as possible. There are going to be a few. Absolutely. Let's take a look. Let's see if it's good or not. All right. This is our actual data from the one we ran. If you look at it's not normal. It's not really a U, but it's not, it's a little U-ish. You got a little bit of height there, a lot of height here. It's definitely not that. That's good. This is good. We got a lot of zeros here. See all the zeros? Got a few zeros over there, not too many. Mostly ones over here. Got a handful of ones here. So we have a fair number of errors, but all these zeros here kind of make up for them.
So what's the x-axis?
X-axis is probability of the outcome. Probability of there being, in this case, an honor student.
And the y-axis is the number of observations.
It's frequency. It's like a histogram. It is histogram. Right? So with me? Right on. Cool. Okay. So final thing is the case-wise list. And this produces a list of cases that didn't fit the model very well. A case is a line in your data. And for most of you, that means a person. So you will be like one of the fights that happened. You will be one of the people in the study, and so forth, right? So SPSS uses the term case as a data element, not element, but a line, a horizontal line is the case. So in this case, we have 1, 2, 3, 4, 5, 6 people in our data that didn't really fit very well. You want as few as possible. Hopefully you get like 1 or 2. 6 is a lot. That's not good. Right? So what does that mean didn't fit very well? It means they're outliers. Now, in the future, when we go back and look at how to process our variables, let's say I'm looking at age as my variable. I'm going to graph the distribution of age in my sample, and if I got like most people are between 20 and 40 in my sample, and I got one guy's 112, he's an outlier. I got to worry about him. That's outlier within a variable. Here we have outliers within the model. Okay, a bit different now. So how are we determining that? If you remember, let's go back a second. If you remember when we chose the case-wise listing, I'll show you in a second because there was a little box there saying what determines outliers. And I think we chose 2 standard deviations as being an outlier. So if these things are happening just out beyond that, we can fiddle with that and see what it is, If there are too many outliers, it probably means you need more variables. It means that a lot of these folks aren't being accommodated within the model. You need more things to explain what's going on. The other way to do it is just take them out, right? And that's done a lot because they're outliers. They're not relevant to my study. Okay, maybe they're genetic freaks or something. But there's lots of them, then it's problematic, right? So in your discussion, you got to say, I got these outliers, and I'll take them out, and I'm a little worried. So they're just deleted entirely. I'm not saying you should do that. I'm saying it's an option. Ideally, you want to analyze further or maybe examine those cases. Maybe there's some missing variables in those cases. Maybe something's been miscoded. Maybe you got someone who's 300 years old. It should be 30, right? That's Usually that's the case in my experience. Is something's been miscoded. But
I actually said, is there a cutoff of like the number of like?
no. Some people will say like 2, right? I don't know. I would say 2 as well, 2 or 3. But
Out of how many?
total. Like,
Total is 10 versus 1,000.
yeah, it's a good question. It's a good question. I don't know. Maybe like I would say 1 or 2%. Yeah. Yeah. I mean.
Where can I go like 2%?
Yeah. I mean, I don't want to give you a hard answer because, again, this is one of the situations where it's very qualitative. There's no rule. There's no strong rules around this. The best thing to do is to show that you've examined why they're outliers, and you accommodate best you can. Okay, so if you look at what's given to you on the Casewise list, you've got residual and Z. This is something called Z resid over here, numbers over here. Do you remember Z scores and normal distributions from stats class? A Z score is the number of standard deviations that something is from the mean. That's all it means, right? So if you remember, a Z score of 1.96 meant that you're 2 standard deviations from the mean. If it's 2.58, it was 3 standard deviations. If it's 3.5, then it's like 99.5% away. You want to set a cutoff that's rational and that's traditional. So we use those numbers because we like whole numbers, 95%, 99%. So 99% of your data falls within 2 standard deviations. Right? 99% falls within 3 standard deviations. The Z values that correspond to those cutoffs of 95 and 99 specifically are 1.96 and 2.58. So the Z residual here is actually a Z score that allows you to see how far these individuals here are from the distribution in your sample. It's a mouthful, right? So first guy number 32, his entire experience in your data set is unusual. How unusual? Well, he's like 2.8 standard deviations away from the mean unusual. That means he's outside of 99% of your respondents. So if you're looking for a cutoff of which people to toss, well, 2.58 is not a bad number. Right? So anytime you got someone who's more than 2.58 away, that means he's beyond 99% of the rest of your group. That's the logic here. And that's why you can toss them and explain to your examiner, look, here's the distribution. He's like way over there. Oh, geez. Right? So, and you remember that originally you chose what the cutoff level was over here. It doesn't really, oh, come on, get back here. Even though you chose that level, that gives you what the table is. You still have the opportunity to look at that visually and say, well, this is a very high number, I'm going to toss that guy. Or this guy's on the cusp, I'll keep him in. But the right thing to do is go investigate who that guy is and see what his situation is. See if there's missing data, miscoded data, and see if you can add in more covariates, right, and see what happens. Okay. Oh, look at those are all the diagnostics. For your homework, I want you to run that regression again, the one I gave you last time, using the same data set, and I want you to examine the case-wise residuals and see if you can make decisions around who the outliers are, right, and solve these problems. There it is. And also read those links I gave you. I'm not here next Monday, so are you guys able to reschedule for another day in the week? So you want to look at it right now to see what's available? Let me see.
Be the last class?
No, I think we have a couple more. If that's okay with you guys. Let me just